Believe it or not, this is lab number 6. And this particular lab is so old that they still at that time called it molecular weight. We know it's molar mass now, but, and sometimes I'll digress, regress into using molecular weight. But we're going to determine the molecular weight, molar mass of an acid. In this case, the acid is citric acid. And we're going to use a titration method. So I guess the first thing to do is find out if you know what a titration is. You ever heard that term?
Not until I got to this lab.
Okay. Titration. Actually, the word titration can go off in a dozen different directions. We're going to use titration in terms of acid-base reaction. Actually, the concept of titration is built upon the ability to equate an unknown substance to a known substance in terms usually of concentration. So if we know, let's be specific. For our acid-base reaction, we're going to have a base, sodium hydroxide, of a known concentration. We have to determine that first because sodium hydroxide is not stable for long periods of time. So the solution has to be recalibrated before you use it. And that's what the first part of the lab is all about. We take acetic acid, which is very stable over long periods of time. And it's a known concentration. So let's take it from there. So this is our unknown concentration. And we're going to use acetic acid. And this is our known concentration in terms of molarity. So we know that this is only going to produce one hydrogen per molecule. This is only going to produce one hydroxyl per molecule. So when they get together in a reaction, we're talking about this arrangement. It's going to produce one hydrogen and one hydroxyl. When they get together, guess what they make? Water, H2O. And then what's left over? Well, it's like a double replacement reaction, right? We just swap partners. So these two got together, so now these two have to get together. Sodium acetate. But that's soluble. So if we know the concentration of this one, and this isn't the exact, it may be referenced in the method as 0.873. We'll just use that. We know that concentration. Now, when you get in the lab, you have to read the bottle, and the bottle will be a different concentration. Okay. So if we know that concentration and we take 10 milliliters of it, of that, how many moles of hydrogen ions can we contribute to this reaction? Well, if we convert that to liters, remember molarity equals moles per volume. So if we want to know moles, we need molarity times volume. Right? So if we do it the old-fashioned way, we say this is equal to 0.010 moles. Excuse me, liters. There we go, liters. I move it 3 places, 1, 2, 3. Yeah. And then if we multiply this times that, what do we get? Well, let's see, we get 8.73 times 10 to the, let's see, that would be -1 minus 3, right? Minus 3 mole. Did I do that right? 1 times that would be 0.8, which would be -1. And then we had 2 parts there. So that should be right. That many moles of hydrogen ions. Or before they react, it would be that many moles of acid. All right, if we know exactly how many moles of acid there are, and we add this unknown, and it takes, I don't know, 25 mils, let's just say. Say this takes 25 mils in order to reach equivalence. That is where you've used up exactly this many moles of hydrogen ions by adding a certain volume there, right? And we know the volume because we have a device that will tell us. We just keep adding small increments until we reach the equivalence point, okay? If that's how many milliliters it took, and this is 0.025 liters, then that one times its molarity would be equal to this one, right? That many moles. This many moles equals that many moles. Okay, so now all we have to do is divide this side by that side, 0.025. Okay. Let's see what I get. So 8.73 exponent -3, and then 0.025 divided into that. So I get 0.35 equals 0.35 molar of the base. Okay. So your book puts it this way. Molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Now that works if there's a 1-to-1 relationship here. Okay. If there's not, if your acid has maybe 2 or 3 hydrogens over here, it won't work. You have to use a different expression of concentration called normality. Or, I'll show you how to do this later, or you use the stoichiometry to tell you how much base you've added. Okay, we'll come back to that in a minute. That's the whole idea behind titration. You have a known, and you add an unknown till you reach a recognizable equivalence, and then you can calculate how much is in the unknown. Okay, so that's probably was a bad choice because the sodium hydroxide, I believe, is close to 0.1 molar. That might be 1 molar. We'll have to see. It's written on the bottle. I think it's 1 molar. Now, how do we know when we've reached that point where they're equivalent? Well, there are 2 ways you can do it. And we'll look at these in more detail second semester, where we actually use a pH meter to draw a titration curve. But that is very time consuming and laborious. So if you have 150, 200 samples to do, which I often have had, you want a quicker way to do it. And we use an indicator, something that will change colors when you get close to that point. So instead of the equivalence point, which is very accurate We want to use something that's accurate enough, the end point. And the end point is nearly always a color change. And you remember reading about what we're going to use for the color change?
It turns pink, doesn't it?
Yeah. Can you pronounce the name?
No.
Phenolphthalein. Phenolphthalein. Yeah, it changes color. In acidic conditions, it's clear. In basic conditions, it's pink. So what we want to do is, for the first part of the experiment, add enough base to our acetic acid solution so that it just turns pink and just barely stays pink. That gets you very close. If it turns just bright pink immediately and there's no equilibration involved, then you probably overshot, right? And it's not uncommon for students to do that the first time around. That's why we're going to do 3 replicants, right? Of each titration, we're going to do it 3 times. So if you mess one of them up, you can throw it out and just average the other 2. Okay, so that's how we tell when we've reached equivalence, is with this color change. Well, how about safety concerns? Well, let's see. There's going to be glassware. Right? The base, the acetic acid is not particularly dangerous. We're essentially using vinegar, 5% acetic acid. So it's not particularly dangerous unless you get it in your eyes or on a cut. But the 1 molar sodium hydroxide is extremely caustic. And it will, if you're wearing blue jeans, it'll make white spots all over. So that's an issue. Broken glassware. We're not going to use any heat. Yeah, just splashing chemicals, basically. That's about all there is. Let's see. All right, that gets into the titration of your citric acid. I was wondering if we had something else we could talk about first. Yeah. I'll bring up the citric acid stoichiometry in a minute. Let's look at the discussion question, unless you have comments or questions.
Did we have to do the discussion questions? I just did the pre-lab.
Yeah, well, they're in the document. Should do the discussion also. Now, are there any there are some post-lab questions? Yeah, there's some post-lab questions. Okay. All right, so here we go. Discussion question number 1. All right, calculate the volume of 0.75 molar sodium hydroxide solution required to titrate 25 milliliters of 0.873 molar acetic acid solution. Since we know that the ratio of base to acid in terms of their contributing hydrogen ions or hydroxyl ions is 1-to-1, we can use this expression. Okay, so what's the molarity of the acid? 0.873 molar, right? 0.873 molar. And how much acid are we going to use? 25 milliliters? Okay. Probably wondering why I wrote that up there and not liters. You can use milliliters in this expression because it's a ratio and the milliliters cancel out. Right? So the ratio between this milliliters and that milliliters is exactly the same as the ratio between that liters and that liters. So you don't have to change it to liters like I did before. Molarity of the base, they say, is 0.75 molar. 0.75 molar base, and this is our unknown. And notice, since the volume here is in milliliters, the volume there will be in milliliters also. All right, so what's the volume of the base? Well, bring this over here. I'll just put the numbers up for now. All right. It should be greater than 25, shouldn't it? Because this is a smaller number than that number. It's going to make it larger than 1. It should give you a maybe 26 something. Let's see what it is exactly. 0.873, 0.75, and 25. Ooh, a lot bigger than I expected. 29.1 milliliters of our base. Okay. How about number 2? I'll leave that one up there. Number 2 says, calculate the volume of 0.75 molar sodium hydroxide solution required to titrate 1.2 grams of citric acid. Now, we can't use this expression because the molarity of citric acid contributes 3 protons each. Right? So it's not going to be useful here because molarity is only the whole molecule, but we're interested in the stoichiometry between the hydroxyls and the hydrogen ions. Right? So one possibility is to change its value into normality, and then it works. But we're gonna talk about normality in the second semester. So I think what we'll do now is use stoichiometry. Right? So the stoichiometry is going to be the citric acid, which is going to have 3 protons, and that's the rest of the molecule. Right? It gives you the formula in the method, but to save space, I'm just going to say 3 hydrogen ions attached to this citric acid. Okay. Then we're going to titrate that with sodium hydroxide. And that's going to yield what? Water and sodium citrate. But since this is 1 positive and these are 3 positives, we need 3 of these, don't we? We need 3 of those to take the place of the hydrogens. So that means we need 3 here, and that means we get 3 there. Okay. So now if we go back to, remember how we did stoichiometry, 1.2 grams of citric acid. 1.2 grams of citric acid. And we want to find out the volume of this one. So it tells us the concentration, which is 0.75 molar. 750 molar. And we want to know the volume of that required to titrate this. Well, how many moles does that represent? Remember, you can't go anywhere in a balanced equation without moles. Right? Grams won't get you there. So we have to go back and look at, we do need the formula, so we can calculate the molar mass. So that's not it. Is it? Here it is. H3 C6 H5O7, correct? Okay. So we can calculate the molar mass of that molecule, right? 3 hydrogens, correct? 1.01 times 3. 6 carbons, 5 hydrogens, in addition to these 3, right? I could have put 8 up there if I'd been thinking in advance. And then 7 times 16 for oxygens. And that will be the molar mass of citric acid. Now, this is the accepted value. We're going to actually calculate a determined value in the lab and compare it to this. 3.03 and then 12.01 times 6. Add that, 5.05, and then 16 times 7. I get 192.14 grams per mole. Okay. So we want to convert this dimensional analysis, want to convert this to moles. Right? We need grams on the bottom, moles on the top. So we put 192.14 here and divide that into 1.2. Since I've still got it in my calculator, I say 1.2 and flop them and divide. And this is 6.24 times 10 to the minus 3 moles of citric acid. Okay. Now that we know how many moles that is, we can use this stoichiometry to find out how many moles of sodium hydroxide we need. Right? It's stoichiometry, just like we've always done. So I would take this one here, 6.24 times 10 to the minus 3 moles of citric acid. And my conversion factor would be, right, denominator, numerator. This would be sodium hydroxide. So this would be 1 here and 3 there, correct? So I just multiply 3 times that value. And I get 1.87 times 10 to the minus 2 moles of sodium hydroxide. Okay. Now we go back to what molarity means. So 0.75 molar sodium hydroxide is moles per liter. Per volume. So volume over here, that goes over there. I divide this number by 0.75. And this tells me 2.50 times 10 to the minus 2 liters, which would be how many milliliters? If we move it back over here, let's move it over here. Yeah, move it this way, then it'd be minus 3. That'd be 25. 10 to the minus 3 times liters is milliliters, right? 10 to the minus 3, 1,000th is a milli. So if we make it like this, messed up. Try that again. Does everybody see what I'm doing here? This is milli, right? This got bigger, so that had to get smaller. So this milliliter, now that I can cancel that out and call it milli, this is 25 milliliters. That's the volume of sodium hydroxide we need to titrate 1.2 grams of citric acid at that concentration of base. So intuitively, we know that since this acid produces 3 hydrogens and sodium hydroxide only produces 1 hydroxyl, it's going to take 3 times as much sodium hydroxide in a molar sense than it does citric acid. That's where this comes in. Okay? Yeah, my Zoominator's in the way, sorry. Okay. So we got that one discussion done. Does that make sense? It does when I do it on the board, right? When you try to do it yourself later, that's when the problems arise. Pre-lab questions. That's why I like to record all this stuff, so you can go back and look at it again if you need to. Phew, it's too much work. Try this. A lot of smearing, but it's easier to wipe up a smear than it is to wipe up a bunch of letters and numbers. Now clean it up. There we go. Okay, pre-lab questions. All right, number one. Calculate the molarity of a sodium hydroxide solution if 24.3 milliliters were required to titrate 25 milliliters of 0.873 acetic acid. All right. As long as the acid and the base produce exactly the same number of their respective parts, hydrogens for the acid, hydroxyls for the base, then you can use this equation. Okay. So now, let's be methodical about this. So we don't get into any trouble. Molarity of the acid. 0.873. Oops. Try that again. 873 molar. Volume of the acid. 25 milliliters. Molarity of the base is the unknown. And the volume of the base is 24.3. Yeah, 24.3. Okay. So it takes less base to neutralize than the acid. So that means this concentration should be greater than that concentration by some margin. So we're going to solve for MB. So that's MABA, oops, over BB. I just held this one there, put this one on the denominator, and then flipped them over. Now we can fill in the values. 0.873 molar, and the volume of the acid is 25 milliliters. And then the base is going to be 24.3 milliliters. Notice I didn't have to change the volumes. Let's see, 0.873, 25 times, and 24.3 divide. So this is 0.898 molar. Okay. So our prediction was right. This is a higher concentration than that one. All right, questions? All right, moving on to question number 2. Okay, calculate the molecular weight of citric acid if 25 milliliters of 0.75 molar sodium hydroxide solution were required to titrate 1.2 grams of citric acid. All right, so here again, we're going to have to, this is taking that discussion question and working it backwards. So we're going to calculate the molecular weight, and it's good to keep this one in your notes because you're going to do exactly the same thing with the results of your lab. So we've got citric acid being titrated with sodium hydroxide, and we know these are all aqueous. So we know that one's going to be 3. And this one's going to be 3. And this one's going to be sodium 3. Like that. Okay. So we're given 25 milliliters of 0.75 molar. 25 milliliters of 0.75 molar was required to titrate 1.2 grams. 1.20 grams. All right. Look at the question. Calculate the molecular weight, or in modern terms, molar mass of citric acid. What do we need for a molar mass of citric acid? We need the mass per mole, right? Okay. So we got the mass right there. We got to figure out the moles. How many moles does that represent? Right. So what we have to do is find out how many moles was required from the sodium hydroxide. And if we multiply 0.75 molar times 25 milliliters, what unit of measure do we get? Did I ever explain that to you? You don't get moles, you get millimoles. Okay. So 0.75 times 25 is 18.75 millimoles of sodium hydroxide. That's what was required to titrate this to the endpoint. Okay. All right, so let's find out how many millimoles of citric acid that represents. Sodium hydroxide on the bottom, citric acid on the top, and this is going to be 3, right? Coefficients, 3 and 1. So 3 divided into that is going to give us the moles of citric acid, millimoles. Okay, so I divide that by 3, and I get 6.25 millimoles of citric acid. Okay, we can't use that value over here because it's not moles. So the easiest way to convert this to moles is to recognize what this means right here. Milli. It means 10 to the minus 3. And that's moles. Okay? Save yourself a lot of headache. Just know what those prefixes mean. Now we can calculate 1.2 grams per 6.25 times 10 to the minus 3 moles. Right? Let's see. 1.2, see, flip that and then divide. Here we go. So I get 192 grams per mole. Right? That was pretty close to what we calculated before. Okay, that's all the pre-lab questions. We talk about the mechanics of the lab. The methods, the procedures. Since no one in here has ever done a titration before, probably ought to talk about that a little bit. Whenever you're going to dispense a liquid, and you need to know exactly how much you dispense, graduated cylinders don't work too well. Because graduated cylinders are designed to contain, they call it TC. You'll see it scratched on the side. TC, and it'll say plus or minus either percent volume or absolute volume, plus or minus. That's the accuracy. Other devices are designed to deliver. We're going to use, one of them is a volumetric pipette. Let's see. Does this thing got pictures in it? No, it doesn't. Okay. So volumetric pipette is the first accurate piece of glassware you're going to learn how to use. I'm going to spell it like we do on this side of the ocean. No, in England, they would put another T and the E on the end. This method may even have it too. Or is it spelled the way we do it? It's volumetric. They spell it the right way. Okay, so what does the volumetric pipette do? It ensures that you deliver within the accuracy of the instrument a known volume of liquid. They're usually shaped like tube, and then they have a bulb in the middle. And then they go down here to a narrow tip. Like that. That narrow tip is engineered to deliver liquid from this device at a steady rate. And that rate is determined by how the liquid, usually aqueous solutions, wet the glass. They'll stick to the glass, but if you give them enough time, they'll drain off the glass and out. So this thing is small enough so it's slow. And it's slow so that as it drains, there's enough time for the liquid clinging to the walls to drain with it. So that ensures the delivery of the known volume. In our case, we're going to use a 10 milliliter volumetric pipette. And it'll have a scratch or a painted line up here. And that tells you that that's your fill point. Okay. So I'll show you how to fill one up. Once you get the liquid in this position at that fill point, and you've got your thumb over that thing right there, or you've got a rubber bulb over it that's locked in place and it won't let air in, so it holds it there. When you get ready to deliver and you move this over to your delivery vessel, then you release that and it starts to drain. It's going to drain down until there's just a little bit left in the tip. That's fine. It's calibrated for that. So with that left in the tip, it has just delivered 10 milliliters, probably within 0.01 or 0.05%. I think it's 0.05% accuracy. They're very accurate, reproducible also. So that's how we deliver our acetic acid. In the first part of the experiment, we deliver a 10 milliliter slug of acetic acid into our Erlenmeyer flask. Remember, the Erlenmeyers are like this. Right? 125 milliliter, they're already sitting on the desk, on the bench top. So you deliver that in there, and then we want to deliver base from a device that will tell us exactly how much we put into that flask. In the beginning, we're going to put it in there with acetic acid, right, to calibrate our sodium hydroxide. But once we know what the concentration of sodium hydroxide is, the next time we use this, we want to put citric acid in there. And then we put some water into it so it'll dissolve, right? And then we deliver again sodium hydroxide from that device. The device we use is called a burette. Okay. The burette is a long tube, long straight tube. I think ours has a maximum capacity of 50 milliliters. And down at the bottom, there's a stopcock, okay, that you control. And you can meter out drop, drop, drop if you want, small drops. And then there's a fine tip here, reminiscent of the pipette. Okay. So we deliver, and you'll notice when you look at these things, they're numbered backwards from graduated cylinders. Graduated cylinders are small volume to large volume to the top. That's because they're designed to contain. They contain this much This is designed to deliver. So 0 is at the top, and 50 is at the bottom. And it's marked off in milliliters. I'm not sure it's 50, could be 50. Big marks for tens, like 10, 20, 30, 40, 50. And then smaller marks, I think it's going to give it to us in tenths. So it may not be 50 milliliters, it might be 25 or anyway. You're going to read, you read this one differently than you do a graduated cylinder. Remember, if you put a certain amount in a graduated cylinder, right, and then you have a marking here and a marking here, you read from the small up. Okay, this one you read from the small down. So if it stops on, let's say that's 10, 20, 30. If it stops like right here, right, and you started up here, then your final volume will be 10, 20, about 25. Your initial volume is 0, so you delivered 25 milliliters. Okay. Or if it's in between a milliliter, then you want to have the ones in the tens position is up here, and then you add the fractions down below. That confuses some students. But and you can, once you've filled it up, and if you start on 0, then you do 1 titration, and then this is your new starting point. So your initial volume will be whatever you determined as the final volume for the previous one, and then you deliver some more, take this one minus that one, and you get your new volume. So you don't have to refill your burette every time you do a titration, as long as you're using small amounts within the capacity of the burette. Okay. I've provided you with burettes that have, let's see, the stopcock turns inside a, let's see, what do we call it? A bearing. And these are designed so that the movable part and the stationary part are both Teflon. So we don't have to worry about tightening and untightening them. I've got another set of burettes in there that are Teflon movable part in glass, and you have to tighten them down and use them. And then when you get finished with them, clean them up, you have to loosen it, because the Teflon is plastic and glass is a lot harder. So if you keep them under compression, then the plastic will flow up into those little holes and you mess up your burette. So I've provided you with the one you don't have to worry about that. Okay. So let's see. Oh, more technology. All right. When you add things in here, and this is going to be your reaction vessel, this 125 milliliter Erlenmeyer. The method says you add some base and then you swirl it. You don't have to do that. I've got magnetic stir plate here. And you have a little Teflon coated magnet down here. And then you have a big magnet down here that spins. And they're magnetically coupled. So when this spins, that thing spins also in your solution. So once you get it spinning, you just add your drops one at a time until you get the color change. Okay. You'll notice at the very beginning, as you add base to your acid solution, that it'll turn pink right around where the drop hit the water. And then it'll go away. And then as you add more and more, it'll stay pink longer. And then eventually it'll go away. What you want is to add 1 drop or a half a drop. It turns pink, stays pink. That's going to be your input. Okay. Think of any questions? Does this say what size the burette is? There's the volumetric pipettes. Okay. Where's the burettes? I know it mentioned the burette, but it doesn't say what size they are. Let's see. I don't see any. Okay, I guess they're leaving that open to us. Oh, when you're prepping your burette, you have to rinse it out. So you rinse it out twice with the solution that's gonna be delivered from it. So we use sodium hydroxide solution. So you put in maybe 5 or 10 milliliters, and then you take your gloved hand and put it over the top and just rock it. Rotate it a third, rock it, rotate it a third, rock it. And then put it back in the stand and drain it out. Okay. They're going to be clamped to a stand with a device that looks kind of like this. And it's got rubber stoppers on it. So you squeeze these things and that opens it up, and then you slide this in, and it gets clamped from 2 points on this side and 2 points on that side to hold it steady. I think this side has the grommets with dents in them, so you want to make sure it fits in the dents. And that if you do that, then it'll be vertical. This is a burette clamp. It's got one on one side and one on the other side because some titrations you need to do what's called a back titration. The reaction is so weak that the reaction, one of the reactants doesn't like to go into solution. So sometimes we have to put it in there as a solid, suspended in a liquid, and you hit it with one acid, makes it dissolve, but then you go back and hit it with the base and find out how much more acid you put in than you needed. And by difference, you can tell where the endpoint is. We're not going to do that. That's too complicated for this course. We're just going to do a single burette titration. And the base will always be in here. For both the standardization step, the first part, and the titration of your citric acid part. So once you set it up, all you have to do is fill it to here with base for your triplets of standardization. And then when you get those done, fill it back up to 0, and then you do the citric acid. Oh, one thing to watch out for. Right? There's a long tube inside this glass piece. And what happens is sometimes you get bubbles caught inside the stopcock. You don't want bubbles anywhere. You want to be a continuous column of liquid all the way down to the tip. So you're going to clean it out twice, right? You're going to rinse it out once, and then you're going to rinse it out a second time. The second time you do, you try to blow out all the bubbles. And then you stop it when the level of your base gets down to about right here. That means your tip is still filled and you've blown out all the bubbles. I'll watch and see. There are techniques for getting them out if they're resistant. And then once you've done those 2 cleanouts, then you fill it all the way back up to here. And probably a good idea to use a funnel. Okay. So that's the technical part. Any questions?